Hello everybody. In this video we're going to look a little bit more at IMFs. We're going to review some of the reasons why some IMFs are stronger than others, and we're going to also learn about a couple new IMFs that you don't typically learn in your honors chemistry class. These are the IMFs that you probably learned about in your honors chem class: London dispersion forces, Dipole-Dipole, and hydrogen bonding. There are a couple new ones. We're going to learn about Ion-Dipole forces, and then some where a dipole is induced by another substance. Induced means created. We have ion-induced dipole and dipole-induced dipole. Let's start talking about dipole-dipole attractions. When you have a polar molecule, you have what we call a permanent dipole. For something to have a dipole, the sum of all the bond polarities have to make sure they do not cancel out. So you want to make sure that the shape of your molecule doesn't end up canceling out that dipole. Remember when we were deciding whether things were polar or not, you would have to look to see, is the molecule symmetrical, right? You're looking to see, is the top different than the bottom, the left different than the right. You want to make sure that you end up with a sum dipole, where you end up with one part being a little bit positive on the molecule and one part being a little bit negative on the molecule. When you get those partial positives and those partial negatives, you can end up with some interaction between those polar molecules. So the molecules end up being slightly attracted to each other. That raises your boiling point and melting point, surface area, viscosity, right? All of those properties we were interested in. Because they're attracted to each other, you would have to put in a little bit more energy to pull them apart from each other. Trying to show you some pictures, right? We usually use these partial positive and partial negative symbols. And we often will use a dotted or a dashed line to represent the attraction. We don't want to use a solid line because that implies that it's a bond, and these are not as strong as bonds. They're weaker. They're a force. Sometimes you can see some nice computer-generated ones like this, where you get to see the gradient between the partial negative and the partial positive. In AP Chem, you'll often be given some data, and they may ask you to compare things. So you can see here the boiling point and the melting points. This one on the bottom, ethane, is non-polar. Compared to a polar one, you can see how much higher boiling point and higher melting point it has compared to a non-polar one. So you can see on this graph, they're showing you as your dipole moment increases, as it becomes more polar, your boiling point would increase. Remember, when you're trying to rank whether things are more polar than something else, you should be looking at your electronegativities. Things that are highly electronegative are drawing the electrons towards them, makes it more unbalanced, unequal distribution of the electrons, makes it more polar, higher dipole moment. Hydrogen bonding is a type of dipole-dipole that's extra strong. When you have very, very electronegative elements like fluorine, oxygen, and nitrogen, you can end up potentially having these really strong dipole-dipole interactions that we give a special name called hydrogen bonding. I wish it had a slightly different name. I think that hydrogen bonding, using the word bond, is a little bit of gives a little bit of confusion. It's not as strong as a normal bond. It is a type of force. It's a type of intermolecular force. It's weaker than a real bond, but it's much stronger than other IMFs. One of the keys here is that hydrogen is also part of this. We will often refer to hydrogen bonding as needing H-NOF lone pair. And what that means is that we have hydrogen bonded with a very electronegative element, nitrogen, oxygen, or fluorine. That's the NOF part. And they will often have these lone pairs, making even bigger difference in electronegativity between one end and the other. Hydrogen only has that one poor little electron, right? It's only making one bond. It only has sharing 2 electrons. So when these very electronegative elements are pulling on the electron, it ends up exposing the proton. And so you get a very large partial positive and a very large partial negative. And since it's a much bigger difference and a stronger partial charge, you end up with a much stronger force possible. Water is a very important example. Water loves hydrogen bonding with things. It can hydrogen bond with itself, or it could hydrogen bond with other things, like ammonia. You can see here we have the partial positives, where those hydrogens are, and we have the partial negatives, where those electronegative elements are. One of the classic examples is DNA. I would never expect you to be able to draw, the pairs in their DNA. But maybe if I gave you these pictures, you should be able to identify where the hydrogen bonding is occurring. So you can see here we have oxygens, and then over here we have those hydrogens attached to the nitrogen. Here we have nitrogen and hydrogen, and over here we have some nitrogen as well. So we end up with these very large partial positives, partial negatives, and they can interact. And that's what holds those strands of DNA together. You can see here we get 3 hydrogen bonds. Hydrogen bonding in DNA is very important because in order for it to replicate, if you remember, the strands have to come apart. And if they were bonded covalently, it would be way too difficult to get those strands to come apart. And they want it nice and spiraled up, right? And so they need to be somehow attracted to each other when they're not, pulled apart. So they need some kind of a force. That's where the hydrogen bonding is. So it holds them together, but it's weak enough that you can unzip those strands when necessary. Here's some more examples. You can see that the molecules will line themselves up so that the partial positives and negatives end up next to each other. Sometimes on AP Chem FRQs, they will ask you to draw in the bonding and the forces and things. And one of the things they're looking for is that you have the partial positives and negatives lining up next to each other like this. So be thoughtful when you're drawing your pictures. We have to remember that the hydrogen bonds are stronger than the typical dipole-dipole, and that results in higher boiling points and melting points than you might expect. They're still not super strong though. Not as strong as a real covalent bond, but stronger than other IMFs. Be careful when you are writing your answers that you are mindful of using the words bonds versus force. When you're saying something is the strongest, make sure you're saying it's the strongest IMF, things like that. Just be a little bit careful of your phrasing. Just some more examples here. You can see this is polar on the bottom, but ethanol has hydrogen bonding, and look at that huge jump in boiling points and melting points. big jump there. London dispersion forces are very weak, but I save them till the end because I think they're a little bit more complicated. London dispersion forces or London attractions are temporary. Okay, they are not permanent. Big deal that you understand they're temporary. We have for a very brief moment in time a slight difference in where the electrons are. They're all kind of on one side versus the other. And so we get a temporary separation of charge. It's not very much. It's very weak, but it's enough that it can have an impact. Even though you learn about these in honors chem, I think most honors chem classes are not very strict with the types of reasons that you have to give for these London forces. In AP Chem, you have to be very careful with how you talk about the amount of London force increasing. You have to say that the size, the magnitude, the amount of London forces increase with the size of the electron cloud and with, quote, increased polarizability. You cannot say that London force increases as it gets bigger. You cannot say London force increases as you get more electrons. That will not get you any points. Now that may work for an honors chem level, but we need to be a bit more precise with our language and a bit more in depth with our reasoning. So we need to talk about the electron cloud size and the increased polarizability. That just means it's easier for the electrons to end up unbalanced, right? But they want that fancy language in AP Chem FRQs. The reason London dispersion forces happen is because those electrons are not locked in place, are they? They're moving around randomly. And if they're moving around, it is possible for them to end up unequally distributed. Make sure you talk about them being weak and temporary. It is important to understand that all molecules, all atoms have London forces because every single molecule, every single atom will have a moment in time where the electrons are unbalanced. It's instantaneous. You might hear that word too, that it's an instantaneous dipole, meaning it just lasts for just a moment. The thing is, even though it's weak, even though it's temporary, once one molecule has a little bit of an imbalance, anything near it will end up also getting a little bit of an unbalance. This can be just enough to make something be a liquid. It could be just enough attraction. I like this picture because they're showing you, like, in this one moment, the electrons are kind of, spread apart on opposite sides. Over here, nice and spread out. And then look what happens here. In this brief moment in time, those two electrons are on the same side, aren't they? And that makes a little bit of a partial negative and leaves the other side a little bit of a partial positive. And in the next millisecond, right, they move, but for that brief instant, this has a tiny dipole. And if it has a tiny dipole, they can line up with each other and have a little bit of force, a little bit of attraction, a little bit of interaction, enough to matter. We need to be careful with our words, right? We need to talk about polarizability. Whether something is polarizable depends on a lot of things like the volume of the electron cloud, which usually is getting bigger as you have more energy levels, right? If you can have high polarizability, you can have stronger IMFs because you're going to have more often a big difference in your partial positive, partial negative, right? Difference in where those electrons are. The other part of this is that the shape of the molecule matters. When you have a larger surface area, you have more places where you can get that temporary dipole, and so you have the potential for stronger attractions. The reason this is hard is that even this more, complicated reasoning is very oversimplified. It takes a lot of, crazy mathematical computer simulation type stuff to figure out, how this is really working. But what AP Chem wants to see is that you've gone one step further than your honors chem class. If you say it's larger mass or you say a larger size, you're going to lose all the points instantly. Very harsh about this. You can see here, these are a bunch of noble gas atoms. Things that don't really want to interact with each other, right? But as the size of the electron cloud gets bigger, as you get more polarizable, can you see what happens to that boiling point? It gets higher, doesn't it? Because you're getting more London force. So the xenon atoms will have more moments and stronger moments where their electrons are imbalanced and they are slightly attracted to each other compared to something like helium. Now this is a picture from a textbook. I don't even know what book at this point, but I have always hated this picture a little bit because I really don't like that they have a column here for molar mass, because mass is not the reason for this. So I've decided to literally cover that up. This is about the size of the electron cloud, the volume of that electron cloud, and the polarizability of those electrons clouds. Not about the mass. So now that picture is much better. So once more, let's fix our picture. There we go. Now, does the fact that you have to talk about the size of the electron cloud and it being more polarizable mean you're having to write a little bit more? Yes. But they are specifically looking for those two things. Now the surface area can be complicated to calculate, right? Surface area is not as simple as you might think. So the types of examples that they would give you should be obvious. You'll have things like a nice compact molecule here, like this nice tetrahedral thing, versus a big long chain. Should be obvious that they're trying to get a surface area difference talked about. They love to give graphs and pictures for these. And once again, what do you see about that terrible thing on the bottom, right? That's a bad thing. We don't want to talk about mass here, right? Don't talk about that mass. The problem is trying to graph something like the combination of the electron cloud volume and polarizability and surface area, right? We don't really have units for that, okay? And so they will often give you a graph exactly like this that shows mass because they're trying to trick people into mentioning it. Don't mention it. That is not the reason. Sometimes you'll see graphs like this that look a little overwhelming. Lots of different lines, lots of different data points. But if you notice, they're talking about boiling point, which means they're talking about IMFs, which means they're looking at things like whether something is polar or not. Look at CH4, how low it is. It's not polar. And then they're looking at the size of the dipole. And to figure that out, you look at electronegativities. And so you see similar patterns. As things get more electronegative, you'll get higher boiling points. They may ask you to explain things that don't quite make sense, that don't follow the patterns, maybe. If it's not following the electronegativity pattern, then it's probably about the amount of London force, or about something being, a hydrogen bond versus a normal dipole. Look for those kinds of things. Now let's talk about some of the new IMFs that you probably haven't learned in Honors Chem. Ion-Dipole attractions is when you have an ion interacting with something that has a dipole. This is why we can have things be soluble. If there is a large attraction between the dipole and the ions, it'll be soluble. You get these water molecules surrounding your ions. You may hear people talk about things like spheres of hydration. That means the water molecules are surrounding those ions. Can be very, very strong. Ion-induced dipole is when you have something that is nonpolar and an ion comes up next to it. The very large charge here can essentially it can induce a dipole where there normally would not be one. This positive charge is pulling the electrons towards it, which results in this now being a little bit polar with a little bit of a dipole. Dipole-induced dipole is when you have a dipole moment, right? You have your polar molecule attracting the electrons in something that's nonpolar, which causes it to have a little bit of a dipole when it normally wouldn't. Now, this would not be as strong as an ion-induced dipole, would it? But it is strong enough to change how things behave. The last few slides are a little bit of caution and then a little bit of summary, okay? So you need to be careful when you're ranking things. Without actual data, you are just making an educated guess. And you might be right, you might be totally wrong. One of the reasons your educated guess could end up incorrect is that we do not always take into account the amount of London forces that exist. If you have tons and tons and tons of London forces, you may end up with higher IMFs than you anticipated. The sum of a lot of weak things can be strong. When you're being asked to rank things, they will either be very obvious, like a nonpolar thing versus something with hydrogen bonding, right? Like very obvious. Or you'll be asked to rank two polar things using electronegativity differences. Or they may give you something with unexpected results. And then you have to look at things like the surface area, or you have to look at things like the amount of London forces that are present, things like that. In Honors Chem, you typically just told people what the most dominant force was. However, in AP Chem, they will often want you to list all of the forces present. You can't just say it has hydrogen bonding. You got to say it has, London force and hydrogen bonding. People feel frustrated sometimes when they don't know when they should list all of them or when they should just list the dominant one. And that's part of reading comprehension. That's where you have to look for key words. That's where you have to read the phrasing of the question. But it's very common to list all of them in AP Chem. One of the very nitpicky things about their grading rubrics is that they are very specific that you need to mention both of the molecules. You can't just list one of them. If a question asks you, why does water have a higher boiling point than carbon dioxide? You need to say something like, while carbon dioxide has London force, water has London force and hydrogen bonding. The hydrogen bonding in water results in more intermolecular attractions, so it has a higher boiling point than carbon dioxide does. You have to mention both molecules, and you have to mention the forces in both molecules. You cannot say something like, water has a higher boiling point because it has hydrogen bonding. Yes, clearly, normal people can figure out that therefore that implies carbon dioxide does not have hydrogen bonding. But that's not how those grading rubrics will be set up. You have to be explicit with mentioning both, the properties of both, and the actual formulas and names of both, right? You can't just say, then the other one. Use the actual formula in your reasoning. So just a real quick overview, right? Our London forces are relatively weak. Everything has London forces. The size, the amount, the magnitude increases with increased polarizability and surface area. And very key that you understand that you can have so many London forces that they add up to be impactful. Dipole-dipole hydrogen bonding have to do with polar molecules. They have that permanent dipole. Hydrogen bonds are very strong. And that's when we have that H-NOF lone pair. I remember that silly little phrase. Ion-Dipole, one of the new ones. When you have an ionic substance mixed with something polar, they can be very, very strong. And it's what kind of explains whether something is soluble or not. Induced dipoles. You could have an ion that induces a dipole. You could have a dipole that induces a dipole. Be very careful with these new ones. The phrasing of these names sounds so similar, but they're not. Ion-Dipole, ion-induced dipole, totally different. Dipole-Dipole, dipole-induced dipole, totally different. Be careful with those. And then remember, we may often have these generic rankings, but you need to be careful that you understand that they are generic. We are way oversimplifying these rankings. All right, everybody, that was a lot, but I hope it was helpful. I hope some of those pictures were helpful and seeing the charts of the data was helpful, and that you now know some of those new, more complicated IMFs. All right, that is it. I hope that was helpful. Bye.